So let us continue with the second type of cable arrangement. You can say cable terminal, flexible cable arrangement. The second type is a catenary cable. Now, in previous discussion we had, if you remember, if you recall, or you can just go back and see the video I just made. The generalized parabolic cable, load was exactly downwards. It was acting downwards. But in catenary cable, now this was parabolic cable. You had minimum loading across, but maximum loading here downwards in field of gravity, because it was holding the pavement. But now when we talk about catenary cable, the only load is from A and B. If you remember where uh, they are used because they are in parabolic nature because of their own weight. This means their weight is quite, uh, you know, not negligible. It is considered quite effective compared to the load they are going to handle. If you remember, you can see this thing when the ship is, or big ships or big vessels are hosted on the bay. You can see these cables hanging from your dock to the ship, and they form a specific slab. This is what this arrangement is called a catenary arrangement. Now, consider this uniform cable suspended from 2 points A and B and hanging under the action of its own weight, right? We will show now today. We will show you the limiting case that these cable assumes a curved shape, and this curved shape under their own weight is called a catenary arrangement. Now, if you look at the free body diagram of this finite portion right here, this very small portion of cable length, let's say S, measured from the origin, which, if you remember last time we talked about the origin is the lowest point of the cable, and this will be considered as where dy by dx is 0, where y is equal to 0 and x is equal to 0. So we have developed in boundary conditions. So the origin of this show, the origin is shown, right? And now this free body diagram differs from the one in that the total vertical forces supports is equal to the weight of the cable section of length S rather than the load distributed uniformly with respect to the horizontal, as discussed before. If the cable has a weight, let's say the cable for this cable, it has a weight of mu, represented mu per unit length right here, and where S is the total length of this small area. So we can say for a very small arrangement, so the reaction force, the resultant force of this small length S would be R, or dr is equal to mu ds, because mu is fixed. So what we get if we take this arrangement and take this relationship of dr is equal to mu ds, and we put this arrangement into the governing equation that we have derived for a generic flexible cable, which would be d2y by dx square is equal to, if you recall it correctly, it would be wx by t naught. Now, if you take this r and you put r over instead of wx dx, right, replace it by mu ds, what you get is this equation, which I am highlighting it right now. Where you should remember, mu is the weight distribution law, T naught is the initial condition at where x and y is equal to 0 right here, and dy by dx is equal to 0. Now we are going to rearrange. Now you have to remember, we are going to develop a relation of ds by dx. So you got w mu dx, and you can find w for ds by dx. This is the value of over mu, and you rearrange it dy by dx, and you will get, after rearrangement, this equation. Now this equation is achieved by simple Pythagorean, or you can say identity. You can say this displacement S is a combination of change in dx along this length and a change in dy to form this arc length S, assuming that our S is very small. So based on this information, we can simply apply Pythagorean theorem, that is ds square is equal to dx square plus dy square. Now you take this arrangement and you put this in the initial equation right here, you will get this equation. Sorry for the noises at the back. GR at home giving lectures from there, so if there is a disturbance, my apologies. Now, let us further continue. From here, we have understood that S is a function of y and x, or x and y. So when we rearrange it, we got this equation, that is the next second equation right here. And now taking this equation and we choose differential form and differentiate it accordingly. You guys can do it by dy by dx, you know, and we solve it from if you remember, in form of differentiation you always have a substitution or technique where you can substitute dy by dx, and in this case dy by dx is substituted by p, so p is equal to dy by dx. And when we do the first order differentiation, that is differentiating the entire equation for dy and dx, as you can say, it is not implicit, it has a mixed information. You can say both the values are in single relationship, so this relation can separate. We are going to find the value of dp by dy by dx, and what we obtain is something not here, but something in the form of, let me show you right here, something like dp by under root 1 plus p square, which is equal to mu over t naught dx. Now this is the relation of dp by dx. You take this relation and you further open it, you will get this relation. And this relation, you have a constant c, and you can put this value of c, assuming that we know at the very bottom or this point at the origin dy by dx is 0. This means p is equal to 0. Then at this value point x is also 0, and you putting the values into these equations, you can find the value of c, which is equal to 0. Now we have a problem. The problem arises, our function is not of p, so we have to change back p into our function into x and y formation. Putting p back into x and y, and what you get is, in fact, I hope you all remember this relation. It's difficult to write with the mouse. Let me try my best. If you have remembered, this is from your mathematics. It is actually an identity you can find from your math book. You can say dy, when you open p by dx and arrange this equation, what you get is exponent mu x by t naught by 2 minus exponent minus mu x by t naught. Sorry, if you remember the identity, this relation is called sine hyperbolic. Yeah, sine hyperbolic. Once you got this relation, your life is going to be easy, since this relation can be exactly evolved. If you remember this thing, you're just replacing p by dy by dx, and you take an exponent value, this becomes exponent, and this will become your sine hyperbolic function mu x by t naught, and c is 0, as we have discussed earlier, so you will get the relation from the exponent form, and this will be dy by dx. And if you simplify this equation, what you get is this equation. Not this exactly, but let me put it this way. It's not here, not this equation. In fact, this is for s. What you will get is dy by dx is equal to sine hyperbolic mu x by t naught. This is what you're going to get once you put back the value of t. Now, we have found the value of this dy by dx is going to provide you the value of sine hyperbolic function. But if you want to find the value of y, what you do is you do it the second derivation of dy by dx. Let me fix this thing again. You do the second derivation of dy by dx, and okay, let us back to the problem again. When you do second derivation, what we have found so far is that dy by dx is how what? Dy by dx is in fact sine hyperbolic as sine hyperbolic mu x by t naught. Yeah. What you do after that is you do again the second derivation. In this time, the integral is 0 to y, dy by dx right on the other side of sine hyperbolic. And what you get is this y, the function of y as a function of x. This will show you your rope design or your rope curve, how it is allocated, how it is spread over a specific length. As you keep on feeding the value of x, it will show you the distribution of y. Now, we need to find the value of arc, that is in terms of s, the small arc s, right here, the actual length of the cable. What y is giving us the shape of the cable, where s is going to be the actual length of the cable under its own weight. So you do the second integration and you put the value of s by simply taking dx by dy as equal to tan theta, and you put this is equal to mu s tan of theta, and you got sine hyperbolic form. And this is what you get when you change. Now remember, this s is directly derived from dy by dx is equal to sine hyperbolic mu x by t naught. All you are doing is saying that dy by dx is equal to tan of theta, and tan of theta is equal to, if you remember correctly, mu s by t naught. So this is where you get mu s by t naught. Now let's move further. Once you have found the value of y, that is the shape of the curve, s, the small segment, how the area or this s is defined in terms of mu x and t naught, we need to find the value of t. What exactly is t? So if you look at this diagram, t is in fact t naught and mu s. So you can say it will form a perfect right angle triangle. So you can say along base you have t naught, along height you have mu s. So t naught square plus mu square s square under root will give you the value of t. This is what you get. And you take this value and you have the value of mu s. You introduce the value of s right here into this function, and this is what you get. 1 plus sine hyperbolic t naught mu x t naught. And then you should remember you are introducing the value of t naught and s into it. As a result, you will get this function, and from there you can simplify, as you all know the identity: sine square plus cos square, or sine hyperbolic plus cos hyperbolic squared. Each of them is equal to 1. And when you reconfigure this thing, this is the final shape of the value of tension you get. Simplifying it again, this is what you're going to get, the value of tension. Now this is a simple formation of the catenary cable design. Now these equations are may seem complicated, but in reality these are the simple derivations. All you will be using is the very basic equation, the fundamental boundary equation, that will be the very first one. The rest are all the relations that you need to know: how the weight is distributed, how the length is found, how different arc angles and positions of the tension across the form it is found. You also need to remember that the maximum condition would hold when A and B are at the same height and are across the same length. Remember the same thing, but in this thing the only thing that is changing is that the weight acting downwards under the action of gravity is the weight of the cable itself, not the load but the weight of the cable itself. In this particular case, the maximum tension or maximum value that has to be found that the rope will be handling is the value of T, not T naught, T. That will be the maximum value. Now we have finished the flexible cables, and next we are going to talk about a few examples that are going to give you a little understanding how to handle the problems of flexible cables.